Let's look at examples of writing ionization equations for modified Arrhenius acids. And to know something is an acid, you have to know that its pH will be less than 7, or the litmus test comes back red litmus test. If you're given any of these properties, then you know that the compound you're referring to is an acidic compound. So the first thing to do is that if a compound is ionic, dissociate it. If not, then we can go to step 2. The second step is to react the hydrogen-containing compound with water to produce hydronium. That's our step 3. Right? We're only going to create one hydronium at a time, even if the compound in question may have 2 hydrogens or more. Okay, so an example here would be dihydrogen phosphate, H2PO4 minus. We're going to react one hydrogen at a time and then react a second hydrogen in a subsequent step. A note here is that we have to watch out for the compound ammonium, NH4, because it has that extra hydrogen that can react with water to form hydronium. Let's look at an example here. We have ammonium chloride has a pH of 5. Now, we're told that it has a pH of 5, so we know it's an acid. So therefore, we must produce the hydronium ion in our ionization equation. Step 1 says we have to dissociate the compound, so here it is. We dissociate ammonium chloride into the ammonium ion, as well as the chloride ion. Next, step 2, we're going to take the hydrogen-containing compound and react it with the water. Well, in the case of ammonium chloride, it's ammonium that contains a hydrogen compound. So, we take the ammonium compound, ammonium, react it with the water to produce hydrogen. Well, what else is left? Right? We have now taken the hydrogen compound from NH4, so it's no longer NH4, but now it's NH3. And NH3, if you remember, is ammonia. So there it is. We have our ionization equation of ammonium reacting with water to produce hydronium and ammonia. And the presence of hydronium ion here is what makes the solution acidic, being pH 5. Let's look at another ionic compound. Here, we're given potassium bicarbonate, and we're told it has, when put into solution, it has a pH of 6.1. So this is slightly acidic. Because it's acidic, we still have to produce hydronium ions. So our first step is to write the dissociation equation. Potassium hydrogen carbonate dissociates into potassium ion and bicarbonate ion. Then we take the hydrogen-containing compound, in this case, hydrogen carbonate. So hydrogen carbonate reacts with water to produce hydronium. Okay, so when we move the hydrogen ions from hydrogen carbonate to water, produce hydronium, what else is left? We're left with carbonate, CO3. It's also important to balance the charges here. We note that on the left-hand side, on the reaction side, the net charge here is -1 and 0, so -1. So on the net side, on the right-hand side, the product side, what's the net charge? We have one positively charged molecule and one molecule that's doubly negative charge, so the net charge is -2. So we have net charge of -1 on the left, net charge of -1 on the right, so we're balanced in terms of charges. You can also think of this in terms of positive hydrogen ions. If you remove a positive hydrogen ions from CO3 negative, the remaining compound must be one more negative, or in this case, -2. Okay, one more example for modified Arrhenius acids. We're told that lithium dihydrogen phosphate here has a pH of 5.8. So 5.8 is acidic. So therefore, in our ionization reaction, we must produce hydronium ions. Our first step, though, remember, is to dissociate lithium dihydrogen phosphate into lithium ion, and dihydrogen phosphate ion. So then we're going to take the compound with a hydrogen, in this case hydrogen phosphate here. We're going to react with water to produce hydronium. Now remember our rule, if a compound has two or more hydrogen, such as dihydrogen phosphate, we're going to react one hydrogen at a time. So H2PO4 now becomes H1, right, PO4. So the other product, of course, is hydronium. Now, if you wish, you could take this product, HPO4, and react with the water again to produce hydronium, but that reaction in actuality, in reality, does not happen very often, so we don't consider that reaction. As well, another point here is, does all of the dihydrogen phosphate turn into hydrogen phosphate? Another way of asking that question is, does this reaction proceed 100%? Does this reaction happen totally, right? And the answer is no, because if you remember, this is not a strong acid. H2PO4 is not one of those 6 strong acids, and only strong acids react 100% with water to produce hydronium ions. One last point I would like to make about weak acids, weak modified Arrhenius acid, is that they can form from what's called non-metal oxides as well. So a non-metal oxides is a molecular compound, so anything on the right-hand side of periodic table, and it's usually a gas. So the example here is carbon dioxide and sulfur dioxide. Also, nitrogen monoxide or nitrogen dioxide will also react with water to produce hydronium. You have to know, though, that these non-metal oxides, they actually do not dissociate because they're not an ionic compound, but they dissolve in water. When they dissolve in water, they react with the water to make a weak acid. So the example here is carbon dioxide. Carbon dioxide reacts with water to produce what is called carbonic acid. And then it is this carbonic acid that reacts with water to produce hydronium. And the other product of this ionization reaction is here hydrogen carbonate. And we can do another example here. We can take nitrogen monoxide, react it with the water to produce H2 and O2. And then we can take the H2 and O2, react with another molecule of water to produce hydronium, H3O+, as well as our HNO2-. Once again, notice the charges here are balanced. We have a net charge of 0 on the left. There are no charged compounds. And then on the right-hand side, we have one positively charged compound and one negatively charged compound, so the net charge here is 0. Let's talk about the modified Arrhenius theory for bases. So if a compound is one of those 6 strong bases, dissociate it and you'll have your hydroxide. So a common example is KOH. When placed in the water, it dissociates into potassium ion and hydroxide ion. And it's the presence of the hydroxide ion that provides for the basic property of a solution. So let's say your compound that you're dealing with is not a base. And remember, a base has a pH of greater than 8 and it turns red litmus blue. So the when you take an ionic compound and you dissociate it, right, then you're going to react with an ion with water to produce hydroxide. Just like polyprotic acids, we're going to react polyprotic base with one hydroxide ions at a time. Let's start with an example of a modified Arrhenius base. Sodium cyanide has a pH of greater than 7. So we know this is going to be a basic compound. So first we ionize the compound. So we ionize sodium cyanide into sodium ion and cyanide ion. Next step, we take the anion, the negative ion here being CN, cyanide, react with the water to give you hydroxide ion, and what's left? Well, in this case, it's going to be cyanic acid. remember we're going to take the H from HOH, water, move it to the cyanide ion to make HCN, and what's left is our hydroxide, the molecule that provides the basic properties. Let's look at another example of a weak base in the modified Arrhenius theory. Sodium carbonate has a pH of 8.2. So first step, we're going to dissociate sodium carbonate into sodium ion and carbonate. And notice here we have 2 moles of sodium ion because in our original equation there is a subscript of 2 in sodium carbonate. Next, we're going to take the anion. Here in this case it is our carbonate, CO3 2 minus, react with the water to produce 1 hydroxide, and what's left? HCO3. So let's track the hydrogen. So one of this hydrogen here is now attached to CO3 2 minus to produce HCO3, and what's left is our OH, which is our product. Also note that the charges are also balanced. On the left hand side of the equation here we have a net charge of -2, and on the right hand side we have also a net charge of -2, being one negative here and a second negative here. So let's complete some practice for our modified Arrhenius equations. I encourage you to pause the video here and try out these equations, and then once you're done, unpause the video and we'll discover the answers together. Please pause the video now. Okay, let's go over the answers. Here we have BaHSO3 has a pH of less than 7. So we know we need to produce hydronium ions because it's an acid. Our first step is to dissociate our compound into barium and HSO3 minus. Then our next step is to take our compound with the H, HSO3 minus, react it with water to produce hydronium, H3O plus. And what's left? Well, we can see that if we were to take the H from HSO3 and now attach it to water, what's left is going to be SO3 2 minus. SO3 2 minus. Next, we have K2SO4, and it tells us that it's going to have a pH of greater than 7. That means we're going to need to produce hydroxide ions at the end. So first step, though, is to dissociate K2SO4. When we dissociate that, we get 2 potassium ions and SO4 2 minus. Then we take our anion, here in this case SO4 2 minus, SO4 2 minus, react it with water, H2O, to produce hydroxide. And what else is left after we make hydroxide? Well, we have HSO4 minus. We can see here that once we remove one of the H from water, it becomes, and transfer it to H or SO4 2 minus, you have hydroxide that's left and HSO4 minus. Our third example, NaOCl, sodium hypochlorite, the active ingredient in bleach, has a pH of greater than 7, so we're going to need to produce hydroxide ions. Our first step, though, is dissociate. So we take NaOCl, dissociate into Na plus and OCl minus. Next, we take our anion, which in this case is OCl minus, react it with the water. In this case, I should have written as HOH, to give you hydroxide ions. And to see what's left, we have to track the hydroxide, right? Or the hydrogen. We have the hydroxide OH, so what's left is this H, and this H has to be attached to the OCl minus. So our other product is HOCl. Once again, let's look at the charges. Here on the left we have a charge of -1, and on the right we have a charge of -1. So our charges are also balanced. Our last example is hydrofluoric acid, HF. Our instruction tells us is less than 7, so we know we need to produce hydronium ion at the end of the day. So we write HF, and we notice that this is not an ionic compound. It is a molecular compound. So it will not dissociate when we put into water. When we put into water though, it will ionize, it will react. We already have our compound that contains an H, so we can react with the water right away. To react with the water, we're going to need to make hydronium, H3O+, and what's left over after you transfer the hydrogen from hydrofluoric acid to water is our fluoride. Only our F- remains. Once again, we notice that the charge is balanced. We have a net charge of 0 on the left hand side, it's neutral, and on the right hand side, one positive molecule and one negative molecule, so the charge is neutral, so the equation is balanced electronically. So there it is, 4 practice examples on writing modified Arrhenius equations. I encourage you to try some in your own practice work.